Hello, and welcome to part 5 of our video series on the unit circle and trig functions. This is probably going to be the last part. If you want more, let me know, I guess. But in this video, we're going to talk about the inverse trig functions. So in parts 2 through 4, really in all 4 parts, we've been talking about trig functions. In this one, we are going to talk about their inverses. And to start, I want to give us a quick reminder of inverse functions in general. I'm going to give us a very simple example to kind of remind us what inverse functions are all about in the first place. And then we'll bring in the trig. So let's say I define a function f of x equals 2x. Now, if I ask you to find f inverse of 4, okay, what is this? This is equal to the x value satisfying f of x equals 4. Okay, so this f to the minus first kind of notation, that's our notation for inverse function. Okay, and the way that it works is you feed it an output of the original function, and then it spits out what was the corresponding input. The idea is it kind of goes backwards, right? So like the function f of x equals 2x, if I plug a 3 into this, then it will send 3 to 6, right? It takes 3 and it multiplies it by 2. What the inverse function then does is it takes 6 and it spits out 3. So you can see how they go back and forth. That's the idea, right? So in this particular case, f inverse of 4, we could figure out is 2 because f of 2 is equal to 4. 2 is the input value that gives us the output of 4 in the original function. Okay. Let's look at maybe one thing to note, and this might make you upset, but don't shoot the messenger, okay? You might recall seeing something, the same notation with this -1 as an exponent, right? You might have seen something like this. 2 to the minus first is 1 over 2. That notation, we're using the same notation, right? We're using this -1 as an exponent here and here. Okay, so whenever you see a function, that's the key difference here. This f is a function, whereas this 2 is a number. If we have a function and you see that minus first notation, that is not the same thing as 1 over f. Okay, whenever we're talking about functions, that's not what this -1 exponent represents. I realize it's confusing and frustrating probably, but alas, there is deep algebraic reasons that it makes sense in which they kind of are the same. But I wanted to make that point here. Don't shoot the messenger, okay? With that said, let's bring some trig into it. So let's say that I asked you for cosine inverse of root 2 over 2. Okay, what is this? This is asking for, so this is equal to the angle theta. I'm actually going to leave a blank for that. I'm going to come back and fill in just a moment. I'm going to put that there to remind myself there's a blank. The angle theta satisfying cosine of theta equals root 2 over 2. Okay. And so cosine inverse of root 2 over 2 is going to be pi over 4, because cosine of pi over 4 is root 2 over 2. Right? Cosine inverse of pi of root 2 over 2 is asking what angle gives me cosine, at what angle is cosine equal to root 2 over 2. Now, you might have noticed, well, obviously you noticed, I said it out loud, and we put a blank here, right? We put a blank here, and that's because if you have a friend, your friend might come up to you and be like, well, actually, the answer is -pi over 4. because cosine of negative pi over 4 is also equal to root 2 over 2. So like actually they're both right. But remember, so this is a key point to remember. We're going to come back to this in just a minute, but for now, let me jot down here. Recall that a function must assign to each input exactly one output. To each input, exactly one output. Right? So you might think that something is amiss here because, well, your friend says that negative pi over 4 could also be the output of this function, right? Cos inverse of root 2 over 2 can't be both pi over 4 and negative pi over 4, because then it wouldn't be a function. Then cos inverse would not be a function. So here's what we do to remedy this. We give a specific interval of angles and assign that to be the range of cos inverse, okay? So this blank that I'm going to fill in, we demand that this angle theta has to be in the interval from 0 to pi, including those endpoints. With that restriction, negative pi over 4 is no longer a correct answer. It's no longer a viable output because it doesn't fall into this interval. Notice this interval from 0 to pi, it's admittedly somewhat arbitrary, but not entirely. So if we go from 0 to pi on the unit circle, notice that we hit every value of cosine exactly once. Cosine can go anywhere from -1 to 1. Each point in this interval, each angle, has a different value of cosine, right? There's no two angles in this interval where the cosine value, the x value is the same. And we've hit each value once. We're not leaving any values out. If we kept on going and went down here, well, now these guys have the same cosine value, the same x value, right? So that wouldn't work. So that is why for arc cosine or cosine inverse, you'll also see these inverse trig functions written as arc whatever. So like cosine inverse will also be written as arc cosine. Personally, I prefer the notation arc cosine because it avoids the confusion that we talked about up here with the notation, but you'll see it both ways. For arc cosine, we use the range 0 to pi. And each of these inverse trig functions, all 6 of them, you can do this, right? We talked about cosine inverse here, but you could do the same thing for any of the 6. They all have their own range, which is chosen just like 0 to pi is chosen because it hits each cosine value exactly once. That's how it works for these others as well. So for example, for arc sine or sine inverse, it wouldn't make sense for us to choose the range from 0 to pi because like these two guys have the same y value, the same value of sine, right? This point here and here, they have the same y value. Plus, we don't get every y value, right? We don't get the negative y values with that range. So for sine, we choose the range from negative pi over 2 on up to positive pi over 2 because we get every y value, every sine value exactly once. When I say we, by the way, I mean kind of the mathematics community. This isn't my personal choice. This is the standard that people have kind of agreed on, okay? Theoretically, one could do it differently, but this is the standard. Okay, so this is how it's done. Now, arctangent, the interval is fairly similar to arcsine. However, we chop off the endpoints. Now, why is that? Well, what is tangent of pi over 2? Well, that would be sine of pi over 2 over cosine of pi over 2. Sine of pi over 2 is 1, and cosine of pi over 2 is 0, so this is undefined. Okay? So that's why we chop off the endpoints on the arctangent range. because tangent of pi over 2 and negative pi over 2 is undefined. Okay. Now for arc cosecant, so this is 1 over sine. Okay. So if we're going to get every value of cosecant, we need to get every value of sine. So it would make sense that we choose the same range as we chose for arc sine. However, note right here in the middle, cosecant of 0 is, well, it's 1 over sine of 0. Sorry, that should be a 0, not a theta. Cosecant of 0 is 1 over sine of 0, which is 1 over 0, right? Sine of 0 is 0. Why? I'm so used to making thetas when I write sine. There we go. Sine of 0 is 0, so cosecant of 0 is undefined. So for cosecant inverse, we do choose basically that negative pi over 2 to positive pi over 2 range, but we have to chop out the point 0. Okay, so that's why we're using these unions. If you remember learning interval notation and you thought, when am I ever going to use this? This is one place where you'll use it. The range for arc cosecant or cosecant inverse goes from negative pi over 2 to 0, union 0 to pi over 2, including those pi over 2s and negative pi over 2, but not including 0. Okay. Arc secant is going to be very similar. Remember, secant is 1 over cosine. So maybe I'll just write down what the result is, what the range is, and I will leave you to kind of reason through it, just like we did for arc cosecant. And maybe I'll do the same thing here for arc cotangent. Okay, that one is going to have same range. Yes, the same range as arc cosecant or cosecant inverse, however you want to say it. You should definitely be familiar with both. So this table I would definitely get familiar with. Hopefully my explanations make some sense. I don't have this table memorized. What I do is when I go through each of these functions, I kind of think about what I outlined before, right? I remember, okay, for each of them, we have this interval where every value is hit once and no value is hit more than once. And we have to watch out for things being undefined. If you keep those things in mind, let me make these more clear that these are unions, not V's. If you keep these things in mind, then you can kind of rederive these on the spot. You might have to remember a little bit which one is which, right? You might have to remember, for example, for arc sine, you might have to think about, wait a minute, do we define it as, or for arc tangent, this is one where you could reasonably do it as something like 0 to pi, but you'd have to cut out something like that. The point is, if you stop and think about it, you can hopefully make this make a bit more sense and make it a little bit easier to remember these guys. Okay. Anyways, I think that I will leave it here. So thank you all for watching. Hope you found it helpful. Hope you found all of these videos helpful. If you want more videos, please just let me know. I would be happy to do what I can. Thanks for watching. Hope you found it helpful. And as with the other things, as with anything in math, a video is great, but it is no substitute for practice. So make sure that you're also doing some practice to really make these concepts sink in. Thanks, and I will see you later.